Just gotta I feel like debugging.
Got them?
Yep.
I have three things to hand out. I graded the quiz. The average was about 4.4, lower than I wanted it to be. And mostly because, I mean, and in some sense, it's not a good test because the first one is you get among everything screwed up. What else am I gonna do? So a lot of people didn't get it right. I mean, for example, some people said, oh, the E field, I know what the E field is. You take Q, 1 over 4 pi epsilon inverse square and direct it. Well, that's for a point source. That's for a point source. It's not for on a plate. You're supposed to put that thing on a plate, spreads out. I mean, oh well. Anyway, stuff like that happened. And so the average turned out to be 4.4. If you have difficulties with my grading, which you should probably, why did I get only 1.5? Well, come and talk to me about it. As a matter of fact, I ask you to come and talk to me about it. So anyway, here is the quiz, all right? 4.5 approximately. Now that isn't a fatal disease because we got 2, 3, 4 quizzes. And don't forget my algorithm is that if you get a low grade on this one, you can raise it up to 6 or 7 if you do well on the other 3, right? You get the average of it and you bounce it up to a much nicer number. So don't feel too depressed about this, but I feel a little bit like, holy smokes, I'm teaching hard and well, anyway. Okay, then the second thing is a rather long section of homework, but it's mostly reading, and then one problem. So if you do read everything I'm asking you to read, you're going to be well ahead of me. So you can read it at your leisure. Okay, that's that, and that's a problem G16. And G16 isn't any of this stuff. It's not magnetostatics. What it is a capacitor that ain't a pure capacitor anymore. In other words, you put charge on it, you got voltage across there, you got epsilon in there, and that epsilon ain't perfect. So it's got not only epsilon, but it has sigma, which means that if you put a voltage across this, there's resistance across there. So you wind up with an RC parallel network. All right, and I want you to talk about that. What's the resistance? What's 1 over the resistance of conductors? We talked about that a little bit in that analog, right? R over G is equal to, G over C, excuse me, is equal to sigma over epsilon, stuff like that. That's what this problem is about. Okay, and then after you get the fields in there, you can calculate the stored energy and all that kind of stuff. So that's what this, so it's basically still electrostatics, all right? It's not this magnetostatic stuff, because I haven't really finished talking about the magnetostatics yet. I'm glad that they used this room since then. They must have, because the screens were down, but they didn't erase any of my stuff. So if you recall, we began here, and I think we wound up approximately over here where I was talking about Mr. Beal and Mr. Savard doing a careful experiment to come up with what is this field. They didn't really discuss it as a field because it was such a new idea. I mean, Faraday had not come up with the field but a few years before. But we talk about it that way, so that's the way I'm going to discuss it. And remember what I told you, the way Beal and Savard did it was they had a big long wire, and then they closed it somehow on the edge of the room, I suppose. And then very close into the wire, they put a magnet. So this is the mother source, and this is the detector. So it's a hybrid kind of thing. It's not fully modern yet. We'll talk about that off the board the next step. And what they did is they found this and the magnet is the current flowing. The magnet always seemed to line up perpendicular to it like that, all the way around. So you can think of it as a circle, and then tangent to the circle is this little North Pole, South Pole complex, a permanent magnet. And in addition, the North Pole always seemed to want to go in a particular direction that had to do with the direction of the current. Reverse the current, that little guy would flip also. So all of that was all recorded, so to speak, by Biot and Savart. And then they also wanted to find out, well, how does it get weaker and weaker and weaker? And they found out by George, if you went further, it would go as an inverse square law, like so. Now, think about it. How did they get a force on a North Pole when there's always a North Pole and a South Pole? How did they find out what the forces are? Well, they're very clever. The way they did it was they said, okay, so it's tangent to the circle. Let's kick it off tangent. Let's kick it off like that. And then what Mother Nature does is she tries to line it back up to be tangent to that circle. And of course, having mass and all that stuff, this little guy would wiggle. He would wiggle like this. It would, with a certain oscillation frequency. Now, if you're close in and the force is strong on this, think about it. I mean, if there's a strong force pulling this one and pulling that one in the opposite direction, and you kick it off, then it's going to wiggle fast. It's going to try and turn. But if you go further away and you have a weak sort of force and a weak sort of force, and you kick it off, it's going to sort of wiggle much more slowly. And that is exactly how they told themselves it goes down, it seems, as though 1 over r squared. A very clever experiment. Coulomb didn't have to worry about that because you can take an individual charge and just move it, and it gets weaker and weaker and weaker as an inverse square. But when you got a North Pole and a South Pole, the two magnetic charges put together can't separate them out. Well, then you got to think of a different method, and that's the method they use. So it was a very clever experiment, and they came up with, now I'll discuss it this way. This is the general picture. In other words, I have a circuit. Well, that's their circuit, but I will just picture it like there's a circuit. I'll call it C1. And later on, we're going to have a C2 when Mr. Ampere comes into the picture. And of course, that circuit is made up of a little current and another little current and another little current and another little current. And it's that DL, well, DL1, that tells me it's directed this way, not that way, not that way, even though maybe in this circuit, DC, if I1 is the same, is the same, is the same, is the same, yeah, the weight is the same, but those guys change, okay? Got that idea? And then what you do is some distance away, well, here's the origin. How do I spell out where this fellow is? Well, I didn't write it. This is spelled out as being at R1. Okay? And then, of course, it changes. It changes. I bet you any money, I'm going to do an integral around this C1 where this is spelling out where the little differential current is. That's exactly what we're going to be doing. But anyway, let's say we put our eye on this little fellow here. And I want to find out what the influence, the tensing up of the universe is due to that little guy right there. Let's put ourselves someplace in space. Well, I'll spell it out by R, just like that, spell out by R1. R1 is where the mother source is. R is where you're sitting and trying to figure out what the B field is, this same thing called the force field, the B field. And I'll call that B, due to circuit number 1, evaluated at that position, that R. So that's a fancy way. And since this is a tiny, tiny little guy, differential, it's probably a differential, it's a little bitty B field. And then, of course, there's going to be another one, and another one, and another one. All the meantime, this R1 changing while you steadily hold R fixed. You know, the same old stuff as we did when we did integrals for electrostatics. Okay? And what they found was, and the way we would write it, they didn't write it this way, the little bit of B field due to the circuit number 1, located at the position R where I want to be, is 1 over 4 pi mu zero inverse. Again, we haven't explained what the hell is that mu zero inverse, but we will eventually. And now, it's, of course, proportional to the current. I mean, if I double the current, I'm going to double that. If I triple it, I'm going to triple it. It's a linear system, so that makes sense. And this is the R minus R1. Oh, that's the directed vector from the mother source to where you want to be. That's familiar to us too from electrostatics. That's, if this was a charge and we had another charge here, that's the way we would spell out the distance between the two. And not only as a distance, but as a vector quantity going from the source to the detector, or whatever you want to call it, the place where we're going to place the detector. So I have R minus R1, that's nothing more than this vector right here. And I dl1, well, that's this vector right here, all right? Now, with the numerator, and then this increases as the distance, and then it decreases as the cube, because this is increasing. So this is really, this is the inverse square law, all right? So that's what they found out. Yeah, it's inverse square, but we're writing it this fancy way. And we're familiar with that from electrostatics too. That's the way we wrote things. Now, but you notice, unlike in the case of electrostatics, where this sort of was the line of sight, in other words, R minus R1 is directed like so, and a force would be, if you placed a charge here, was in the line of sight. Well, this one is weird. It isn't just line of sight. There's this cross product. That is the way you explain why the forces are tangential to the circle running around the current itself, right? That does it. Okay, and that makes electrostatics look a little, magnetostatics look a little bit more complicated, because, you know, most people don't like cross products and all that stuff, but you gotta have it. That's the way it is. Mother Nature says it isn't like that. It isn't like that. It's like that. Okay, and then inverse square. Now, of course, that's just a little bit due to that little bit of mother. Well, now what you do, as I said, you're going to integrate all the way around, all the way around. Of course, a circuit has to be a circuit. That's what it means. It feeds back on itself over the mother circuit of this differential dB1. And there it is, right? So this is the way you find the B field due to a mother source. All right? Got that? Any questions at this point? This is really Biot-Savart, but they didn't write it this way. This is the modern way of writing this. But this is the tensing up of the universe due to a current flowing around on a contour C1, okay? And gives it the direction and the size and all that other stuff. You want to change where your position is, change the R. I'm no longer at this R, I'm at that R. But you still do the integral on the 1. See, so that's what I call a DL1. This is, you do it on this variable, not on this variable. This one is held fixed. And there shouldn't be, conceptually, it should be the same as electrostatics. This should be familiar to you, how you do that sort of thing. Now, at this point, let me, so to speak, start again at this end. And say, okay, so now I got this tensing up of the universe. If I was in electrostatics, what would be the next step I would do? Well, what I would do is I'd say, how do I detect that thing? I would put a detector in there. In the case of the electrostatics, so here's a cloud of charge, rho volume free, and I go over here and I get an E field at R, like so, and this is, again, this is R, and this is R1, and you integrate over R1, and you get the E field over here at your choice of R, and this is R minus R1, something like that. Same picture as we have. But what would you do if you wanted to detect that thing? Don't forget, there's nothing over there. It's just the tensing up business. That's Faraday's idea of the field. What you would do is to get the force on that thing, let's say at R, like so, you would take that E field and multiply by the little test charge, right? That's the detector. That's the detector of the E field. And you would reconstruct Coulomb's law, as if you had a Q here and you had some sort of Q over here. That would be essentially Coulomb's law. So you get back to Coulomb's law, but you do it in a two-step process. First, from the mother's charge, you get the tensing up, the E field, the force field, and then the second step is you multiply by whatever choice you have for the detector. This is the detector, all right? Now, you can do the same thing here. What you can say, and this is essentially in newtons, and so if you want to divide by the Q, this is given in newtons per coulomb. It's a force field, newtons per coulomb. Now, when we played around with voltage and stuff, we found it would be more convenient to talk about volts per meter and stuff like that. But it's really a force field, and the newtons per coulomb tell me that it's a force field. Well, the B field is a force field also, but and you tense up the universe not with a charge sitting there like that. You tense it up with a charge moving around on this contour right here, and you tense up the universe with this B field. It is also a force field. But how do you detect it? Well, I used a charge before, so I'll put a charge right there and find a force on it, right? No, that's the wrong kind of detector. Just a Q is not the right thing. We're in the magnetic world now. So what you do is you place a north pole there. That's what you do. Of course, you can't get a north pole. Every time you try and get a north pole, you get a south pole also, don't forget. But we can pretend and say, oh, in the old classical way, the way you get the force is simply to take the B field. So I won't reproduce that picture over there, but here's that B field. B1, let's say, due to that circuit 1, evaluated at R. Again, all that business in that picture. And then you put a north pole. What do they call it? Maybe like a Q magnetic or something like that. The strength of a north pole. Okay? If you want to put a south pole, it would be like a negative. It's just like a charge, only I'm thinking of it as something different than a charge. It's a north pole. I don't know what a north pole is yet, and I can't really get one. I mean, whenever I put a north pole in there, I get a south pole too. That was the problem these guys had. Every damn time they got a north pole, they get a south one too. So, I mean, they had a complex. In other words, a dipole, a magnetic dipole. Remember that? We use that word in electrostatics too. So there is something different. You can't get a north pole. But in the old way, the force at that R would be equal to the force field and multiplied by this north pole strength. Well, and that was analogous to all the electrostatics. That's the classical way of looking at it. Now, you can't get one of these, so the classical way is not a practical way. So around Biot Savart did their work around 1820. But 5 years later, took a while, down in Paris, I mean, those guys were French. In Paris was this guy, Ampere. In about 1825, Ampere wrote a paper, a very famous paper in Compte Rendu, the fancy French scientific journal. 125 pages, I mean a big, long paper. Not just on this subject, but he did all kind of amazing things in that paper. But one of them was to say, well, you know, I have an electric circuit causing a tensing into the universe, and yeah, I can detect that with a north pole. But I think that what you can do is you can also detect it with another current. In other words, you do away with that north pole crap. You just put another current here. So the picture then becomes two circuits, and that's why I call it C1 and C2. So we have something like this. In this paper, he described it. He made, I guess, I can't read French very well, but he made some mistakes, but the mistakes were trivial. But you have essentially a C1 with all this I1, DL1, all that business. And then here is the B field, and then you place a second circuit, and I'll just picture it, you know, there's another circuit, C2, and with a current flowing on it, let's say I2, DL2, something like that, same. Again, the distance from here to here directed is like so, and the usual positioning, this would be R1. Well, this is circuit 2, so I guess I could call that, instead of R, call it R2, and it's all that same sort of thing. And this is now the detector. Now, of course, if you want to, this is a detector over a pretty big, you know, the B is different here than it is here, than it is there, than it is there. And if you want to find it at one point, you would just make a tiny little circuit, right? You would just make a little loop right around here. And that's what he actually did. He made a little coil like that and found out that that little coil of current, I2, looks just like a North Pole, South Pole complex. The permanent magnet. Only this is what we would call an electromagnet, huh? I mean, you remember all this stuff from your physics, I hope. So that would detect the B field over there. But I've pictured it here as not just a little guy, but as some other kind of circuit. And I'm trying to find what the force is on this circuit, okay? And Ampere says, oh, okay, the little bit of force on circuit number 2 is equal to I2 DL2 crossed into, damn cross again, equal to the crossed into the B due to circuit number 1 located at R2. In other words, that's this B right here. And you get a little bit of force on, well, maybe I should do it in red again, this little bit of current. Right? So you integrate all the way around this guy, a la that thing at the very bottom over there, and you get the B field here. And then what you do is you take, and that's the B field due to circuit 1, and you're positioning yourself at R2, where you want to be, should be underbarred, like that. You take the current, you take the current, I2 DL2, and cross the two together, and you will get the force on that little guy. Of course, that's not at all. I mean, you have to then, if you want to get the whole force on the whole circuit, you would integrate this all the way around circuit 2, and you would get the force on the second circuit, and that would be essentially like that, all right? And this is the differential. You're integrating around C2, second circuit. The strength, if you double the strength of that current, well, sure, then the force is going to double. If you double this one, it's going to double this thing, and so it'll quadruple. You know, all that kind of stuff follows through. And it should be underbarred, like so. This is called Ampere's force law. Now, he has another very deep other law, but this is the Ampere's force law, and that tells me how much force is on the second circuit. I call it the detector circuit, due to the presence of a mother circuit, right? And there's no North Pole, South Pole here at all. And if you want to think of this little guy as a coil, then you can almost make, as I did, an analogy of an electromagnet to a permanent magnet, if you want. We might play with that a little bit later. Okay, this is Ampere's force, and that, the forces, of course, are in newtons, like so. So if you think of it, this is in newtons here. This is in ampere meters. So the B field has to be in newtons per ampere meter. I mean, that's what the B field units are. But we never write it that way. We always say the B field is measured in Tesla. Tesla, named after Nikola Tesla, that Serbian-Croatian genius. So this is measured in Tesla. But if you want to look at the units here, newtons, amperes, meters, then this thing has to be in newtons per ampere meter to make that newtons over there. And that's the fundamental thing. But then we call that Tesla. Okay? After Nikola Tesla. Now, Tesla is a pretty big unit, actually. In the old days, when I was a student, they called the units of the B field Gauss. They named it after that German mathematician Gauss. Now, it turns out that 10,000 Gauss equals 1 Tesla. But they somehow, that's what it is. And we used to talk about in terms of Gauss, and now we talk about it in terms of Tesla. But sometimes you still hear about Gauss. You know, like for example, maybe you don't. Maybe you've never heard this, but you know, again, maybe I'm going back to your high school physics. How can you take a piece of iron and magnetize it? How can you do that? One way to do it is to take that piece of iron, little rod, and keep rubbing it, keep rubbing it, keep rubbing it, keep rubbing it. I mean, it'll go slow, but keep rubbing it, and you'll have a North Pole and South Pole permanent magnet after a while. If the iron is, as they say, soft iron, easily magnetized. Let's say. Now, think about this. There I am in a big destroyer, a big ship, a military ship, let's say, floating through the ocean year after year, year after year, year after year, rubbing the water. The ship is iron, steel. The water is rubbing, rubbing, rubbing. What happens is that damn ship becomes magnetized. Just like that piece of iron that you keep rubbing, it becomes magnetized. Now you might say, who the hell cares? Well, the bad guys know about this, of course, and they say, oh, I think I'm going to invent a mine, an explosive device to get that guy that is sensitive to the magnetic field. So here's the magnetic field in the ocean caused by Earth, Mother Earth. That's a big magnet, you know. North Pole, South Pole, permanent magnet. And then this ship comes along and disturbs it because it's a little magnet in the presence of this Mother Nature big magnet, changes the magnetic field. And that mine picks up on that, explodes, and wipes out the ship, okay? So it's very important to recognize that the ocean water passing over this ship over a long period of time can magnetize a ship, and that magnetic ship can essentially change the B field enough to maybe be detected by some nefarious device floating around. This becomes important, you know, that Strait of Hormuz where all that oil comes through by the Arabian Peninsula and stuff. The Iranians are thinking of putting mining the thing. So mines are still, you know, they're not old-fashioned, they're still around. And then so what do you do? What do you do to do that, to compensate for that? Every so often the ship will come into port and they will wrap, I guess it's done automatically, a great big coil around it and then force the B field of the electromagnet to exactly oppose the B field of the ship's permanent magnet and cancel it out. And if you do that in the right way, you start with a big current, you slowly oscillate the current and get it smaller and smaller and smaller and smaller, then the ship is demagnetized. And the name that they use for that is they de-Gauss the ship. So they still use the word Gauss, but they could use the word they de-Tesla the machine, the ship. But they still use the word they de-Gauss it. Interesting, huh? And when I learned, we didn't even have Tesla. I mean, we only talked about Gauss when I was a kid. Okay? There's the story behind everything. All right. Let's see. I shouldn't have erased that damn thing. So the problem, similarly to the field technique in electrostatics, is take the mother source, get the E field, the tensing up of the universe. In this case, take the current, the mother current, get the B field, the tensing up of the universe, and then place in that field the proper detector. In the one case, it would be a charge, and in the other case, it would be another current. So it's a two-step process to get the force on the detector, right? A two-step process. Now, I won't write it all down here because it's in your notes. So the first step is use Mr. Beal and Mr. Savart's law, this thing here, to get the B field, B1, at R is equal to R2, okay? And then, when you got that, use that formulation I2 DL2 crossed into that B and do the integral around the red circuit, the second circuit. So it's, again, a two-step process. And I might ask you to do that in a test, or maybe make up a homework problem. But in this sense, let's say I give you the first circuit. Let's use Beal-Savart. I mean, a big, long, straight wire closed over here. And make it so long that that's infinite and that's minus. In other words, an infinitely long I1 DL1, causing a B field everywhere, right? And it's going to be, you know, around and around and around like that, getting weaker and weaker as you go further away from this infinite current source. And then I place there another circuit, let's say C, this should be red, a C2, right? And I ask, how much force is caused on that thing? Well, I would have to essentially get the B field here and 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 here. And I do all that, get the B field there. Easy to do, actually, you'll see. And then use that cross product. The I crossed into the B would give me a force on this wire. The I went after I've integrated from here to here. Then the same thing here. The I crossed into B is going to give me a force on this. Similarly here, similarly here. All right, like that. And then the sum of the forces is going to be the force on. Now, the assumption is, of course, and I probably won't write this on a quiz, but the assumption is it's a rigid. This is rigid. It doesn't squiggle around as like, let's say there's a force on this and it begins to misshape and that misshape. No. Let's make it rigid body. Okay, so that would be a test of you getting the B field from a mother source, away from the mother source, and then applying Ampere's force law, where you put a second circuit in there to get the force on that second circuit. And then, of course, the other thing is I might ask you, oh, no. I don't want that force. I don't want the force F2. I want the force F1. And what you would say is, oh, I know what I'm going to do. I'll call this C1 and this C2. And then I will get the B field due to this part, this part, this part, this part, here and here and here and here, and then I'll integrate around this whole damn thing, and I'll get this force, which is absolutely true. You would get that. But that's a tough integral to do, it turns out. The other integral is, we'll actually give this as an example, I think. This is the first way to do it is much simpler than the second way. So, and in this force is the negative of this force, just like in the case of two charges. This force and that force are the negatives of one another, right? In the opposite directions. So why not do the easy one and then say, oh, that's equal to the one I really want, okay? This is nothing new. We saw that in electrostatic sort of thing. It's just that we have a little different math and, of course, different mother source and different detector currents and stuff like that. Do I have questions here at this point? You're so quiet. You're supposed to not understand this stuff. Okay. All right. So the last thing I want to say is, hey, a B field, just like an E field, is a vector quantity. You've been talking about, these underbar, the size of it is inverse square, proportional to the cross products, and all that kind of stuff. But what direction is it in? And So let's talk about that, and I think I mentioned it here. Right-hand rule gives a direction of B. In other words, if I take, I don't like this one is kind of, well, I take the direction of the current, okay, there's the direction of the current, and I cross it into, what is this, R minus R1? Oh, that's this vector here. So I take this vector and I cross it into this vector. If I do that, I hope you use your right hand correctly. If I cross this guy, the current direction, into the direction from the mother source to the point of interest, if I do that, then it's into the board. In, all right? And I pictured it there as in. And you can always depend on that. You can depend on that right hand. Now, when the current goes around, and let's say I take this is the same current running around, and I do the same thing here, and now this is the R minus R1, and this is the direction, then I get essentially this thing crossed into the R minus R1, and that's out of the board, right? Like that. Got it? Got it? Hey, do you agree? Do you agree? This is important. Now, this one is closer to this point than this one is. So I'll bet you any money that the B field due to this fellow, yeah, he's out, whereas the other one is in, but he's not as strong as the one that's in. So if I think in terms of these being close and giving in, and these being far, giving out, I'll bet you the ins beat things up. And you can say, like I could ask you just a simple question. Tell me which direction the B field is in. And you could, thinking about it, you say, well, that's the close in stuff. And so that gives a bigger B field. So I'll figure out what direction that is with the right hand. And then this will be from the right hand, and that's weaker field. So I'll bet you any money it's in. In other words, a very simple answer, but you have to think about it. Now, I suppose I could give you some crazy circuit like that and say, what does the B field? Well, you can't tell there, you know? I mean, that one would not be possible to use this very simple right hand and stronger here and all that business. But in something like that, you certainly could. Like, for example, if I gave you that and I asked for the B field over here, this is going to have a strong influence, that's going to have a weaker influence. This will be strong for the current over here, but that one is also strong, it's going to give you in the opposite direction, and this was weaker. So I'll bet you any money, again, if the current was like so, and so the current is like DL1, something like that, this crossed into that is going to be into the board. I'll bet you any money that over here will be into the board. Got it? Question?
So if you reverse the current direction, what would happen?
Then you reverse the current, then you reverse the B field.
So it would be going out.
Then it would be coming out,
What
in
about
that case.
What about the influence on the edges of that square that you just drew? Is it gonna be the same influence, the same strength?
The influence of what now?
Like the edges, like you said, the closest it is, like the current?
But if you figure out that this is out, edges included and all that stuff, and you reverse the current, I don't even have to think about it again. It reverses the B field. Now, what you're asking me is, how much influence does this current and that current have with respect to, let's say, this current? That's what you're really asking. And then if this one beats those out and it's out, then if you reverse the current, then this will beat those out too, reversed. Now, I would say that because this is so, the influence, as a matter of fact, is mostly going to be not even this current here or that current so much, but it's basically from here to here because it's so close. Now, if you're far away, like that where that's far and that's pretty far, but pretty close to being the same. Well, now you got some questions there. Then you have to actually do the mathematics probably. So I'm giving you a simple way for a simple shape. Like for example, and I think I did this. I made this picture in your homework handout. Let's say I had. Well, no, yeah. say I had this coordinate frame, Z, Y, X, and I had something like this. A circle, and then a little circle, and I'm asking for the B field over there. Something like that, with the current flowing, let's say around. I'll bet you any money, because this half circle is closer into the place, that whatever direction the B field is in, and what direction is it in? Well, current, with your thumb in the direction of the current, in, right? So it's in due to all of this stuff. And how about this one? Oh, I put it, and that's, if I put that in there, it's in. Now, if I think, no, let's put the current like this. Let's do it like that. So now the current is coming like that, coming like this. And now the current is out. And this one is in. But this one is close, this one is far, and therefore I bet you any money this one is going to beat that one. You know, that sort of thought process. Use it. Okay? Now that's not getting you the numbers, but it at least says, I know what direction it's going to be in for this very special case. And now you might say, oh, how about this and that? I mean, there's current flowing there too. Well, it turns out, well, I should go back to the right here. I2DL, no, I1DL1 crossed into the B1 at R2, integral all the way around and all that kind of stuff, C2. The current direction is in the same direction essentially as the, in other words, the current direction, if you had, let's say a circuit like this, the current direction is in the same direction as the line from the source to the detection point, then the cross product of two parallel things is going to be equal to 0. So you can always be guaranteed, if I give you a current like this, there it is, starts here and stops there, and I ask you, what is the field over here at the end? Gonna be 0. Don't have to even think about it. It's gonna be 0. Now, not true over here, or over here, or any place else, but along here, any place is going to be equal to 0, okay? And that's because of that wonderful thing, actually, the cross product. The thing that you think is your enemy is your friend here. I point all that stuff out in my notes, in examples that I give. Just before page 190, I added some notes, page 1, 2, 3, 4, 5, 6, 7. Some examples of shapes of current. What kind of shapes? Very simple shapes. A line of current, you can't have a current like this. What I mean is, there's no current, and suddenly 5 amperes, 5 amperes, 5 amperes, and then nothing. I mean, you can't have that. But let's make a thought experiment. So there is some sort of a current, I1, DL1, and all that stuff. And then on the bisector, that means halfway from L over 2 minus L over 2, here I am at 0. On the bisector, a distance, I think I call it rho, what is the B field here? Well, if the current is up, for sure it's into the board. So if that's, I don't know, if this is the X direction, it's in the minus X direction, right? Right? Yeah, okay. And then I give you the fancy formula. I won't write all these out, because on a page, I think 192A and B, I give you a little summary of all of these, what the B fields are. I'm building to a crescendo here. But here, on the bisector of a finite length of wire. Now, of course, you might say, hey, I could make that L get really big, called infinity to minus infinity. And that makes it and then, what's the bisector of something that's infinitely long? it doesn't make sense to even talk about it. So there, it's only dependent on, I mean, if this is infinitely long, it only depends on how far away you are. I'm over here, I'm over here, I'm over here. You don't care where you are. It's just a distance the bisector, but that formula for the bisector one goes to the proper value if the line is infinite. Very simple. The B field depends on, in this particular case, that would be the phi direction, I suppose. Do you understand what I'm saying? What if I go away here? Well, that's the phi direction, or the phi direction. I mean, you know, Biot-Savart kind of thought. And it's equal to the current I1 all over 2 pi, this mu0 inverse, and then inverse related to the rho, to the distance. It goes as 1 over the distance. This is for an infinite mother source, okay? Question back there.
So if the magnetic field is going to be like a ring around...
Yes, it will be a ring around. Just like I say, just like Biot-Savart found, yes.
But in reality, does magnetic fields really have a direction? Is it just a ring around it?
Well, when I say a ring around it, I mean tangential. Think of it as little vectors that are tangent to that ring. That's the B field. So it is pointing, yes. So when you write that circle around, you got to put a little arrow on it. And that arrow direction is given by the right-hand rule. So that, for example, if I put my thumb in the direction of the current, the B field is in here. It's in that direction there. It's in that direction there, all the way around. Do you understand what I just said?
Yes.
Yes or no? For sure?
Well, yes, but I'm just wondering, like visually, I'm just saying that the magnetic field is just it's a ring, and as you get farther away, it's going to get weaker.
It gets littler and littler.
But is it really spinning clockwise, or is that just a convention that we created? Like,
Now, when you say spinning,
I mean,
it's not really spinning. No, it's
Well, I
just
mean-
it's just there. You know.
Is it just talking about the force exerted is going to be in that direction? The force that it exerts on other things is...
If you put a north pole right there, it would be in the direction of the B field. That's the old classical way that I mentioned, that we don't do it. Okay? If you put the Amperian way, the way Ampere thought about it, if you put a little coil there, that's C2, the second one, it looks almost like a north pole, south pole, and it would align itself up. And I'll tell you how. If you take a little coil, the little coil always lines up so that the most amount of B field goes through it. It wouldn't line up like this. It would line up like this, where almost all the B field goes through the little coils. You understand? It's trying hard to line up that way. I'm going to talk more about that when I get into iron. Okay? Maybe I'm getting ahead of myself here. But this is that infinite one in particular is very neat, because I can make up all kind of problems for you. Like I mentioned to you, I could, this would not be an unreasonable quiz problem. Take an infinite C1 with a current, let's say I1 DL1 going up to plus Z here and from minus Z infinity here. And then I place C2 like that. And I'll put a current, current, current. And I'll name it 1, 2, 3. Find the force on this one, find the force on that one, and find the force on this one. And that's given by whose law? Ampere's force law. It would be essentially this I, this I crossed into the B field of this. And what is the B field of this? I just told you what the B field of this is. I mean, that's why that's a nifty one to have, because it's such a simple B field. But then you have to do essentially the cross product. This, let's say this is up, and the B field is in here, right? And then this up crossed into the in, which it would be, I guess, in that direction, wouldn't it? Yeah, looks like it would be in that direction. And then this one would be in that direction, and this one would be a little bit up and a little bit like so. And the upward one would be equal to the downward one, turns out. It turns out. In other words, this little guy, this little second circuit, will have no force trying to scoot it up and down. There's no reason to do that, because this is an infinite wire. Okay, so everything up here is same as here, so you don't even know where the hell you are with respect to infinity. So I bet you that force bucks that force. You'd have to show that with your force law. And then this one, well, look, this one, all along its length is close. The B field is strong. The current is the same here as it is here as it is here. So I'll bet you any money this is a strong force tugging it in. And this one, well, this current is kind of close too, but this one is far. So I'll bet you any money this force is smaller than that force. And this thing is going to want to suck in toward the mother source. You see what I'm saying? Again, you can reason all of that stuff out without doing numbers. And then, of course, I might ask you for the numbers themselves. But the point is that this is a very nice, convenient, although impractical, C1, because the B field is so simple for this one. If you take a look at my notes at pages 1, 2, 3, 4, 5, 6, 7, if you had this finite, and you were sort of on the bisector, first of all, I had to talk about on the bisector, then the B field here, 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 here is much more complicated. So the math, you wouldn't learn anything new, but the math would be more complicated. So why would I do that? Question?
For that shape.
For that shape,
The half circle one?
this one,
Yes.
those
Where's
two
your
half
B?
circles.
Yes, where is your B?
What's that?
The B, where is the B?
At the origin.
Okay, so we have two currents, what's,
One is going one way, the other one is going the other
so how
way.
did you do the thumb rule, the right hand thumb rule?
Well, if you look at my home, I get you what the B field is on, here's a circle in the plane. I get the B field on the axis of the circle. And if you make that come down to here, you get the B field in the center of the circle. If you notice, this is in the center of that circle, well, not a half circle, and this, it's also in the center of this. So I have formulations for the B field for this one and for this one. Take a look at my pages for the circle, the current that's running around on a loop.
But if they're opposite currents, wouldn't it cancel out?
No, because this one is bigger, because it's closer, inverse square, than this one is. That's the point I was trying to make. You understand what I'm saying? If you had something like this, a current coming down, and then a loop, like this. Here comes a current. And let's say the resistance, let's say it's practical, so the resistance of this is the same as, what would happen? If this was I, this would come out I over 2, and this would come out I over 2, right? 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 Unless this was made of copper and this was made of aluminum, well, then the resistance are different, and one, the path of least resistance, all that jazz, would hold. And then, of course, the current continues on here, I is equal to I1 plus I2. Or I should say, 2 times I2, I guess, huh? Well, here, they're going singular. Well, what direction is the B field right in the center? Well, it's in. What direction is the B field due to that have? Out. And because the currents were the same, they would cancel. In that case, because the distance from this half circle is the same as the distance from this half circle. Understand? So again, you could, without even calculating anything, you wouldn't want to do any mathematics here, because you could say, oh, it's 0. Right off the bat. And if I gave you that kind of problem in an exam, I would ask you to please write in English your reasoning why it's equal to 0. Don't do any math, please. You understand what I'm saying? Don't use your left hand. No, not use your right hand. Okay, so use your right hand here, use your right hand there, putting your thumb in the direction of the current, and then your fingers will go in the direction of the. Now, did I hear? According to that, it's only quarter after. Oh my goodness. 14 according to my thing. Okay, all right, that's enough, I think. We'll see you on Monday.
I have a quick question about this. Okay, so like the current is the same,
the same.
All the currents are the same.
So he says